All right, now that we talk about pay-to-public key hash, now it is time to talk about multi-signatures. So let me give you a brief description. Multi-signature protocols allow a group of signers to produce a single signature on a message M. So that is our idea. Verification of the validity of a purported signature can be publicly performed given the message and the set of public keys of all signers. Several use cases for multi-signatures exist, including low-trust escrow services and split device security. And I will actually talk more about this. A trivial way to transform a standard signature scheme into a multi-signature scheme is to have each signer produce a standalone signature for the message M with its private key and concatenate all the signatures. So this is the most obvious way. So we want M people to sign a message. So we can ask them to sign them independently, and then we can concatenate all of the signatures. But of course, this is not a good idea because the size of such multi-signature grows linearly with the number of signers, right? Because instead of a single signature, if you have 100 people, then you will have 100 signatures. So the size will be 100 times larger. Ideally, a multi-signature scheme should produce signatures whose size is independent from the number of signers and close to the one of an ordinary signature scheme. So this is kind of a dream, and actually this is what we will talk about Schnorr key aggregation algorithm at the end, okay? So again, 10 people can get together and provide 10 different signatures, but if we can somehow combine all of their keys and convert them into a single key, single public and private key, then it will be fantastic because we will provide a single signature and everybody can also provide that single public key from all of the non-public keys and check the validity, okay? So this part we will talk about when we move on to Schnorr signatures. But first, let's look at how this multi-signature works in Bitcoin, okay? So there are many application examples. I took them from Bitcoin Wiki. So let's look at one of two versions of this signature. So this means that when we talk about M of N signatures, this means that there will be M public keys, but M of them will be enough to claim the Bitcoin, okay? So in this one of two, this means that the account actually belongs to two people. So in this example, the husband and wife, they have a petty cash joint account. So both of them have their public keys, which are involved in the transactions which are paid to them. But since this is one, any of them can actually spend them with their own private keys. So this is actually how it works in traditional banking, right? You can go and get a joint bank account with your partner and any of you can spend it. But if you do it two way, and again, this is in practice in traditional banking, people do it like savings account with their partner. So in this scenario, both of them have to agree when the transaction has to be done, right? Because they can withdraw money whenever both of them agrees to do it. So this is why two signatures out of two possible signatures are required. In this case, one signature from out of two possible public keys is enough, okay? A different example is 2 out of 3. Here the example is parents' savings account for child. So in this scenario, 3 of the people, husband, wife, and the child has a public key. They all have a public key, but one of them is not enough to spend the money. So child cannot withdraw money without the consent of any of the parents, okay? One of them is enough. So child can just convince one of the parents to withdraw the money. 2 of 2, again, the example is two-factor authentication wallet. This is really important because most of the time people simply use a single signature case like the examples that we talk about in the previous lecture where we talk about pay-to-public key hash. So if you have a single signature, most probably you have a software on your mobile phone or on your laptop, and this is where you actually send and receive your money, right? These are where you perform your transactions. So if a Trojan actually affects your computer or your device, people can get a hold of your account and, you know, send your money to themselves. So in order to avoid it, 2 of 2 signatures is a good idea. So now you have wallet software both on your laptop and on your mobile phone. So both of them have 2 public keys. But in order to perform a transaction, you have to get signature from both devices. So even if one of your devices is compromised, the attacker has to get to the other device too. This way you can actually, you know, guard your savings. Another example is 3 out of 5. These are just examples when people do it in low trust donation address. So they're like 5 person in the organization, but 3 is enough to spend the money. But of course, in this scenario, when the transaction is performed, you see which 3 people signed the transaction. So there isn't any secrecy here. So this is the important part. 2 out of 3 buyer seller with trustless escrow. So this is one of the basic examples when people first talk about Bitcoin. So assume that you are actually performing a real world commerce. So you pay your money with Bitcoin, but in real world, maybe you are actually buying something. So in this case, for instance, you are the buyer and the seller is promising to send you some product, but if you send the money, maybe the seller won't send you the product, right? So you cannot trust them. So in order to do it, actually you get a escrow. So instead of creating the signatures with the buyer and the seller, actually buyer, seller, and the escrow public keys are used, and this transaction is performed. But in order to withdraw the money, 2 people is required. So for instance, when the buyer pays the money here and performs this transaction and sends the money to these 3 public keys, and if the seller is actually misbehaving, buyer can convince the escrow. So the escrow signs the transaction with the buyer and send the money back to the buyer. So this is how it works. And here the escrow cannot do anything with himself because one signature would not be enough to do anything. So this is the idea. Again, a similar example, 2 out of 3, a board of 3 directors, they're maintaining funds for their organization. 2 of 3, improved hot wallet security for businesses. 2 of 3, decentralized cold storage vault. So these are actually how to, you know, store your money on a cold or hot wallet. We will talk about them in the future. 2 of 2 again can be used for smart contracts building block, such as Tumbleweed, CoinSwap, and Lightning Network. And 1 or 3 out of 4 distributed backup. This is actually means that you can actually give some of your friends some public and private keys. So if something happens to you, 3 of your trusted friends can get together and, you know, save your money. That's the idea. Okay, so there are many use cases for multi-signatures. So let's see how it works. The general form of a locking script setting an M of n multi-signature condition is actually follows. So there are n public keys. So you have to put the public keys here. And you say that M of them are enough to you know, claim this money. So this is actually what your transaction looks like. So n of the public keys, then n, and then the opcode check multisig. Here n is the total number of listed public keys, and m is the threshold of required signatures to spend the output. Okay, sometimes we call m the threshold. So for instance, a locking script setting 2 out of 3 multi-signature condition is as follows. You write 2 and provide 3 public keys, then 3 op check multisig. So this is how traditional 2 of 3 multi-signature looks like, okay? And in order to claim this kind of transaction, so this is the locking part. So in the unlocking part, you have to provide 2 signatures, at least 2, because it says 2 here. So the preceding locking script can be satisfied with an unlocking script containing pairs of signatures and public keys. So your signatures, 2 of them is enough. Here I said A and C, but actually any combination of 2 signatures from the private keys corresponding to the 3 listed public keys are enough. So instead of AC, you can say BC or AB. So all of the scenarios are correct. But strange thing is that you might see a typo here. There is 0 here, right? But I didn't do it unintentionally. So I deliberately put a 0 here. And the problem is that because there is a bug in this opcode. The problem is that whenever actually you create M of n multi-signature, so this opcode actually should expect M input, right? But there is a bug in there, so it expects M plus 1 input. So a common way to avoid this is to put a 0 input at the beginning. So this is a quirk of Bitcoin. So we can actually correct this. Everybody knows that this is a bug and we can correct this, but this is in the consensus algorithm. So if we correct this now, this means that we are creating a hard fork. So instead, we decided to learn how to learn with it, okay? So don't get surprised if you see zeros in front of this kind of transactions, okay? So a validation scripts look like, again, 0 here. Again, here we have 0 due to a bug in the opcode. So you provide at least 2 signatures, and in the original script, it should be like this, 3 out of 2, and these are the 3 public keys. So this check multisig actually looks, it doesn't care about this first input and checks if 2 signatures belongs to any of these 2 signatures, public keys, okay? So this is how you spend such a multi-signature. Now, although this is a fantastic idea, we have seen many use cases. Now, the problem is that it is not a good way of doing it because multi-signature scripts are cumbersome to use. What I mean is as follows. The script has to be communicated to everyone that are going to pay. Think about it in this way. So you have this kind of an account. This could be your, wife and husband account or your, end directors and that kind of account. So whenever somebody wants to send money to you, they have to put this at the locking part of their script. So you actually have to send this part of code to them whenever somebody wants to send you money. So the script has to be communicated to everyone that are going to pay to you. So this is one hard way. The second is that they have to use special Bitcoin wallet software with the ability to create custom transaction scripts. So if you just install a basic wallet software, it will only allow you to send money to a simple single wallet address. Here we are actually listing n private key, public keys, and so on. So in order to support that kind of custom transaction scripts, you need to have an advanced software. This is the second hard part. The resulting transaction would be about 5 times larger than a simple payment transaction because this script contains very long public keys. The burden of that extra large transaction would be borne by the customer in the form of fees because when somebody wants to send it to you, they have to put very long amount of data at the end of their transaction, and the transaction size increases, and this actually affects the fees, right? The person who is trying to send money to you have to pay more fees because of this reason. Moreover, here the UTXO means that unspent transaction list, okay? Every miner actually keeps the list of every unspent coin in all of the wallets. So a large transaction script like this would be carried in the UTXO set in RAM in every full node until it was spent. So this is a bad thing. So you are actually increasing the RAM usage in the full nodes. All of these issues make using complex locking scripts difficult in practice, but we have a solution which is called P2SH. shortened as P2SH. This was introduced in 2012, as you can see 3 years later than the introduction of Bitcoin, as a powerful new type of transaction that greatly simplifies the use of complex transaction scripts. So let's see how it works. But from the name, you can understand that instead of paying to a complex script, you are actually paying to the hash of that script. Okay. So let's look at what we mean by pay to script hash. So traditional Bitcoin addresses began with the number 1. This is what we have seen at the beginning. When we do the base 58 encoding, all of these traditional Bitcoin addresses started with 1. Anyone can send Bitcoin to a 1 address, but that coin can only be spent by presenting the corresponding private key signature and public key hash, right? So far, this is what we've discussed. So you have to provide your public key and your private key signature, and this way you can spend that money. Bitcoin addresses that begin with 3 are pay-to-script hash addresses, but sometimes erroneously called multi-signature or multi-sig addresses. This is because not every pay-to-script hash address is a multi-signature, okay? But most of the time we use it for that purpose. They designate the beneficiary of a Bitcoin transaction as the hash of a script instead of the owner of a public key. So instead of providing a wallet address, which actually corresponds to a public key, you are actually giving a base 58 encoding of a hash of a script. So this is the good part. So you can fill the script and whether in any way you want, so that you can actually create very complex transactions. Okay, they designate the beneficiary of a Bitcoin transaction as the hash of a script instead of the owner of a public key. The feature was introduced in January 2012 with BIP 16. So this BIP actually is a short way of saying Bitcoin Improvement Proposal. Actually, since this is an open source project, you can actually provide your own proposals to improve Bitcoin, and you can actually add new features to Bitcoin. But all of the developers should agree with you. And even if they agree, the people who use them might not agree with you, okay? So even if you add to something to Bitcoin, maybe all of the miners might say that, okay, we are not performing this update, and we will use the previous one, okay? So actually there's kind of a, democracy in this way. So not there isn't any ruler that actually enforces you to use the property or not. Okay, unlike pay to public key hash, funds sent to 3 addresses require something more than the presentation of 1 public key hash and 1 private key signature as proof of ownership. The requirements are designated at the time the address is created within the script, and all inputs to this address will be encumbered with the same requirements. So you create the script and take the hash of it. So all of the requirements are included in that script. So anybody who can, provide that kind of script that provides that hash can span these transactions. So a pay-to-script hash address is created from a transaction script, which defines who can span the transaction output. Encoding a pay-to-script hash address involves using the same double hash function as used during the creation of Bitcoin address, one applied on the script instead of the public key. So that is the whole difference. Here in my first slides, I put the public key here and provided the, 20-byte wallet address that starts with 1. Here I'm putting the script here and obtain again 20 byte. And when I convert it into base 58, I will put a different prefix to it. So it will start with 3 address. So the resulting script hash is encoded with base 58 with a version prefix of 5, which results in an encoded address starting with 3. This is why all of the 3 addresses actually belong to some script, and all of the 1 addresses belong to a public key. Okay? So this is how you distinguish them. So let's see the benefits of using pay-to-script hash instead of those multi-signatures. The pay-to-script hash feature offers the following benefits compared to the direct use of complex scripts in locking outputs. Complex scripts are placed by shorter fingerprints, in other words, are 20-byte hashes, right? In the transaction output, making the transaction smaller. So this way, actually, we save space. Scripts can be coded as an address, so the sender and the sender's wallet don't need complex engineering to implement pay-to-script hash. So this is actually one of the main benefits, because anybody using a simple wallet software can send you money now, because instead of the one address, now you are providing them a 3 address, and that's all, right? So they just transfer money to you. They don't care what kind of a complex script is behind that wallet address. They don't even know. Pay-to-script hash shifts the burden of constructing script to the recipient, not the sender. Again, this constructing the script is hard, but now the receiver have to deal with it. Pay-to-script hash shifts the burden in data storage for the long script from the output, which is stored as the unspent transaction outputs, to the input stored on the blockchain. So this is one of the other benefits. And pay-to-script hash shifts the burden in data storage for long script from the present time in the payment to a future time when it is spent. Moreover, since the size is small, pay-to-script hash shifts the transaction fee cost of long script from the sender to the recipient. Because if you use multi-signatures, not pay-to-script hash, the sender has to provide those long public key addresses, right? So they have to deal with the fee. Now they actually provide a 3 address that starts with 3. So their transaction is really small. So they pay very small amount of fee. But when you want to redeem that money that belongs to you, now you have to provide the script. Okay. Whenever you want to redeem your money that is paid to a 3 address, you have to provide the script at that time to unlock it. So now you are providing a huge input. So the fee now belongs to you, not the sender. That is the whole idea. So let me finish with this slide with some misconceptions and with some warnings. Not every pay-to-script hash is multi-signature, okay? So because a pay-to-script hash is actually, you are paying to a hash of a script. You don't know what the script is consists of, right? But if it is a multi-signature script, then yes, it is a multi-signature, but not always. So pay-to-script hash is not necessarily the same as a multi-signature standard transaction. A pay-to-script hash address most often represents a multi-signature script, but it might also represent a script encoding other types of transactions. So this is the whole idea. So don't think that all P2SH is a multi-signature. But now we have to do some warnings. Pay-to-script hash locking scripts contain the hash of a redeem script. So you have the script, you compute SHA-256 and RIPE-MD, so you end up with 20 bytes, and this is actually hash of your script, right? So this is what you use to redeem it, which gives no clues as to the content of the redeem script itself. The action will be considered valid and accepted even if the redeem script is invalid. You might accidentally lock Bitcoin in such a way that it cannot later be spent. So this is the main problem, okay? Because since you are providing hash of a script and nobody knows the script, they cannot check if the wallet address that starts with 3 is actually a valid wallet address. So if you want to transfer money to a 3 address, all of the full nodes would accept it as a valid address, but actually maybe there isn't such an address. And actually this happened in real time that I saw. I gave a talk like 2 months ago about Bitcoins, and somebody contacted me after the talk, showing me that he was trying to receive money from some exchange website, and accidentally he pressed the wrong button when he was typing his wallet address, which starts with 3. I think instead of A, he pressed G because it looked like the same to him. But this way, they actually paid to him this money to a hash of a script, which we don't have. We cannot construct such a script that would give that wrong hash address. So around more than 1 Bitcoin actually lost because it was sent to an address that doesn't exist. Okay. So without breaking the discrete logarithm problem or primary resistance of hash functions, we cannot actually redeem that Bitcoin. So it is lost forever. So we always say that there are 21 million Bitcoins at most that will be produced, but maybe a huge amount of them are already lost because maybe they are sent to wrong addresses, maybe people lost their private keys, so there may not be actually that many Bitcoin around. So this is a very important thing. So if you are using a 3-wallet address, you have to be sure that you type it correctly because there isn't any error detection here. But in the previous ones we had, so this was the important part, okay? So pay attention to that. But another thing you have to be careful is about, since you have to provide the script whenever you need to redeem it, you have to store all of your P2SH scripts so that in the future you can redeem them. This is actually also another burden on the recipient, right? You have to store them someplace. So generally we only ask people to store their private keys so that they can use their wallet addresses whenever they want. But in this scenario now you also have to store your scripts and so on, which provides a little bit more burden. So these P2SH hashes provides many use cases and many benefits, but also there are some cons in this. And also governments don't like this kind of addresses because whenever you send money to a 3 address, no one knows the script. So if nobody redeems them, you don't know where that money goes to. Okay, so forensics investigators are really angry to this. They have to wait until somebody spends this script money and they have to check where the money goes. So this is why some governments don't like this kind of addresses. Moreover, if you look at the blockchain, you can just look at the wallet addresses, and just by looking at the beginning of them, if it is 1, you know that it is a public key. If it is 3, it is a hash of a script. But in the next hour, I will talk about Schnorr signatures, where actually you will have 1 addresses, but actually you will be performing multi-signatures because you're actually aggregating keys and it looks like a single key at the end. Okay, so if everybody adopts this key aggregation, probably we wouldn't see 3 addresses where people use multi-signatures for. Okay, but again, this provides some kind of anonymity because until you use your P2SH money, nobody knows who it belongs to. So it provides you some kind of anonymity, but this kind of anonymity is also something governments don't like. So you have to be careful, especially you have to be sure that you write your wallet address in a correct way. Otherwise, you can send it to a non-existing wallet address where nobody can redeem it.